Dear friends, we will see now illustration number 9 from the textbook of chapter number 6. In this example, we are given that all the conditions that are provided in example number 8, suppose we follow the path and the condition as shown in the figure of illustration number 9. It is given that an object is tied with spring on the base of the ground. The spring is tied with it. The normal force is acting in upward direction. Now the spring is having extension, that is of a force kx in a right hand direction, and due to the friction the force acting that is also in the direction, that is mu mg, that is a frictional force acting on it. Now here the surface is having some friction, some strain in it. We explain that as given in example number 8. What is now our example number 8? To simulate a car accident, auto manufacturers study the collision of moving cars with mounted spring of different spring constants. Consider a typical simulation with a car of mass 1000 kg. So here we consider again the mass is given, that is mass is 10 to the power 3 kilograms, moving with a speed of 18 km per hour. So here V is 18 km per hour is already been converted into 10 meters per second on a smooth road and colliding with a horizontal mounted spring with a spring constant 6.25 into 10 to the power 3 Newton. So in example number 1, the road was smooth. The spring constant is given, that is K is given by 6.25 into 10 to the power 3 newtons per meter. Now it is also given that if the surface has a coefficient of friction, that is mu is equals to 0.5, then calculate the maximum compression of the spring. Now in presence of friction, both the spring force and the frictional force act as soon as to oppose the compression of the spring as shown in the figure as in above figure. Now we invoke the work energy theorem rather than the conservation of mechanical energy. The change in kinetic energy is, that is delta K is equals to Kf minus K initial, that is 0 minus 1/2 mv square, because ultimately it should stop. The work done by the net force is, that is the work done by net force is minus 1/2 kxm square minus mu mg into xm. Now from this equation, these two equations, when we get the solution, when we try to solve these two equations, we can have the relation that is about K and W. So as per as work energy theorem, we can say that W is equals to delta K. When we try to equate it, what we will get, that is that 1/2 k x m square plus mu m g x m is equals to 1 half m v square. Now when we compare, mu mg is a given, that is mu is 0.5, mass is 10 to the power 3 and g is taken as a 10. We can have that mu mg is 0.5 into 10 raised to 3 into 10, that is about 5 into 10 to the power 3 Newton. So that is known value. After rearranging the above equation, we obtain the following quadratic equation in the unknown xm. So now we can get the unknown equation for xm in the term after the simplifying this equation and making xm as a subject of the term. So what we can get, as here we can write it the term by simplifying the above equation. We would like to simplify this equation in a quadratic term. What can be written? That if we simplify this, we can get k xm square plus 2 mu m g xm minus m v square by 2 is equals to 0. So taking LCM here and we simplify the term, what is the ultimate answer that we can have? That is k xm square plus 2 mu m g xm minus mv square is equals to 0. That is the equation that we have obtained over here. And by doing this, when we simplify this term, we can have the equation in term of xm, that is equals to xm is equals to, that is minus mu mg plus mu square m square g square plus m k v square and raised to 1 half and over k. So these terms out to be this equation as xm, where we take the positive square root since xm is positive. Putting these numerical values we obtain, if we put all the values, we get xm is equals to 1.35 meter. So this is the first xm that we can obtain. If the two forces on the body consist of a conservative forces Fc and a non-conservative force Fnc, the conservation of mechanical energy formula will have to be modified by the work energy theorem. So in that case of conservative and non-conservative force, we can have the equation that is Fc plus Fnc into delta x is equals to delta k. Now that Fc into delta x can be written as minus delta v, as we have already studied. Then we can simplify the term and write here, that is that delta of kinetic energy plus potential energy is equals to F non-conservative force into delta x from the simplification, and ultimately we can say that this is the change in a mechanical energy, that is equals to non-conservative force into delta x, and therefore that E is a total mechanical energy over the path. This assume the form, that is E final minus E initial is equals to force into displacement, that is work done by non-conservative condition. Here WNC is the total work done by the non-conservative force over the path. Here we should note that unlike the conservative force, WNC depends on the particular path from I to F. So this is the resultant equation of the given question. Solution number 13, that is also on the basis of the collision. So first of all, we will consider the collision in two dimension or an elastic collision. Here we consider M1 to be M moving with speed V. It collide with a stationary ball, that is M2, that is having the mass M also. Now when they collide, one of the ball moves in upward direction in the pocket and the other ball goes in this direction by keeping the condition as in the figure. So suppose this is the ball, that is called Q, will move in this direction M1 with mass M, while the target ball moves in the direction M2 as given in the condition with V1F is the condition or velocity of first ball, V2F is the velocity of the second ball. But what is the condition that will happen in this case? Here we have to see whether the ball will move in the direction of M1 or V1F or not. So first of all, we consider that for the momentum conservation, since the masses are equal, we can say that V1I, this is V1I, and already V2 is 0 initially, so is equals to, that is V1F plus V2F as shown in the figure. Now we can, by using the kinetic energy theory also, we can write it, that is if we take the square of this term, that is if we take the square, that is V1I square is equals to, we can simplify by dot product, that is V1F plus V2F into, or a dot, V1F plus V2F. Now taking dot product of both the vector quantity. So when we take dot product of this vector quantity, obviously we can write this is V1F square plus V2F square plus 2 V1 dot V2, that is V1F, and dot V2F vector. Now this is the condition as given. If we simplify the term with the given condition, we can have the equation is equals to, here it is important to note that we can write this condition as V1F square plus V2F square plus 2 V1F V2F cos theta, and that cos is given, that is with a theta 1 plus 37 degree. So they have given us in the condition, as we go with the question, that consider the collision depicted in figure 6.2 here, that is in the figure, to be between two billiard balls with equal masses m1 and m2. The first ball is called the cue while the second ball is called the target. The billiard players wants to sink the target ball in a corner pocket which is at an angle theta 2 is equals to 37 degree, and assume that the collision is elastic and that a friction of a rotational motion are not important. Obtain theta 1. So we want to find out this theta 1, what will be the theta 1 condition. Now we also know that when the masses are equal, then the angle between them that will be 90 degree. So it is very clear, and the masses are as equal, we can compile this equation, that from above equation, if we say that since the collision is elastic, the m1 and m2 is equal, it follows from the conservation of kinetic energy that kinetic energy conservation law is also follow. And for the kinetic energy, we can say that v1f square, sorry, v1 I square. So here we will put the term v1 I square, v1 I square is equals to v1f square plus v2f square. So we can replace this term in above equation at place of this. So it can be written in term of v1 I square. When v1 I square is kept, then obviously this v1 I square can be cancelled out with the term. That means if we put v1 I square is equals to, in place of this term we can put v1 I square plus 2v1f into v2f cos theta 1 plus 37 degree. Now obviously this cancelled out and gives us 0 is equals to cos theta 1 plus 37 degree. So obviously cos is 0 when angle is 90 degree. So we can say that therefore theta 1 plus 37 degree is equals to 90 degree, and therefore we can get that theta 1 to be a 53 degree. So this would be the angle for theta 1 that is asked to find out. Dear friends, now we will see the exercise example number 16. So exercise example number 16, that is given with three figures. We are given in the condition that two identical ball bearings in a contact with each other and the resting on a frictionless table are hit head on by another ball bearing of the same mass moving initially with speed v. If the collision is elastic, which of the following is possible result after the collision? That we are given three figures for them. Initially we consider that one ball is given, it is given a number 1, it is moving with velocity v and collide head on, that is with the contact with the other two balls which are resting on a smooth surface. So here ball 2 and ball 3 are those ball bearings which are in contact with each other and were on a rest. Now the condition 1 is given, that one will come to rest. The first condition that they have given, that one will come to the rest and other two, that both others will move, that is 2 and 3 both will move with the speed v by 2 on the surface. Second condition is given, that one will come to the rest, second will also remains to the rest, and that means both will remains at rest, and third will start moving with the speed v. So this is the second condition given. And third possibility that they have provided, that all the three balls, that is ball 1, ball 2 and ball 3, all the three balls will start moving with speed v by 3 on the surface by remaining in contact with each other. So which of the condition out of these three is possible? Let me check. That let m be the mass of each ball bearing. So we are given that the mass of each ball bearing is same. So if mass is to be m, then before collision the kinetic energy of the system, that will be, before collision we can say that before collision the kinetic energy is equals to 1/2 mv square, and that other balls, that means both the 2 and 3 are stationary, and therefore we will have only the one object as in a motion, that is ultimately this is equals to 1/2 mv square. So this is before collision. Now after collision kinetic energy of the system is remains same. Now we check that whether in which condition it is the same. So that after collision, because in elastic type of collision kinetic energy is always conserved. So after collision, suppose in case 1, we consider that case 1, we check. In case 1 it is given that both the balls start moving with speed v by 2. So now the kinetic energy is equals to 1/2 m v by 2 square plus 1/2 m v by 2 square, whether it will be v square by 2, that is 4, and that is 1 by 8 mv square plus 1 by 8 mv square, that is 1 by 4 mv square. So in case 1 it is not possible. So case 1 has 1/2, in place of 1/2 it is 1 by 4. So case 1 is not possible. Now let's check case 2 after collision, case 2. So what will happen in case 2? We say it is K1, now K2. That is 1/2 m v square. So here it is conserved, that kinetic energy. So this case 2 is possible. Now let us check case 3. What does this case 3 says? In case 3 we say that kinetic energy in case 3, that will be 1/2 m v by 3 square plus 1 by 2 m v by 3 square plus 1 by 2 m v by 3. So 1/2 m v square in a new condition, the velocity is v by 3. So ultimately this answer would be, that is 1 by 2 3 times m v by 3 square, that is about 1 by 6 m v square. So here also the kinetic energy does not conserve. So Out of all the cases, only this is the case in which kinetic energy is conserved, while in all other cases, that is in case number 1, kinetic energy does not conserve, and in case number 3 also, the kinetic energy does not conserve, and therefore we can say that we can apply for case 2, which is only possible case. Now after this, we will move further to the example number 17. Now that example number 17 is also an oral example. We can orally answer it. It is given that a bob capital A of a simple pendulum releases from 30 degree to the vertical, hits another bob B of the same mass at rest on a table as shown in figure here. So I would like to show one figure. Here one ball is resting with mass m on the surface. Here it is resting. The same mass, same length, another ball comes and hit it with certain speed. It arrange at angle 30 degree. So the question is, how high does the ball A rises after the collision? Neglect the size of the bobs and assume the collision to be elastic. So if we consider elastic collision, we can say that the bob A shall not rise, because this is because when two bodies of same mass undergo an elastic collision, their velocities are interchanged. So the after collision, ball A will come to the rest and ball B would move with the velocity of A, and then in the figure shown here, the new condition will be something like this, that 2 will reach to the position of 1, while the previous one will move with the speed of 1. So this ball 2 will come to the rest like this. So this will be to the rest. Now it will become to the rest. Initially this was at rest. Now it will start moving, and here this ball will remain at rest. So this would be the condition for the case example number 17.